Our next speaker is Hadass Inbar, who has worked with Professor Markus J. Buehler at MIT. She will speak on mechanical properties and adhesion of the collagen-hydroxyapatite interface in bone.
Thank you very much. This summer I had the privilege of working under the guidance of Professor Buehler and studied the interactions between the protein and the mineral phase in bone. So, bone is the load-bearing framework of the human body, and it serves a variety of functional functions such as synthetic, metabolic, and mechanical ones. And it is mainly built out of two main constituents, which are the hydroxyapatite mineral and the collagen protein. And these two main building blocks form a complex hierarchical system, and where each level has its own functional property. As seen here, the lowest level that was examined in this research was of the amino acids, which then assemble into three polypeptides that form the triple-collagen protein, which is basically a triple helix. And then when these collagen proteins assemble in staggered arrays, they form the collagen fibrils. And in the gaps between the collagen fibrils, there is a mineral phase of hydroxyapatite. The last structure that is found in all types of bone is bone fiber, which is basically, again, those mineralized fibrils staggered in arrays, and in between them there's extrafibril matrix of protein. So in this study, I wanted to examine the interactions between the collagen and the hydroxyapatite, and basically understand what happens when collagen is sheared across the surface of a nanocrystal of hydroxyapatite, and decide whether it depends on the size itself of the crystal. So to do this experiment, I used steered molecular dynamics simulation, which is a great computational method that enables us to predict the behavior of a system when it is under load, meaning that we combine both experimental data that is already known to us as well as theoretical calculations. The initial system itself, as shown here, is the collagen molecule placed above the fixed hydroxyapatite. The collagen was then pulled in the right direction here, and as it was sheared across the hydroxyapatite, we wanted to examine these changes in its mechanical behavior. And the hydroxyapatite itself had three models. We had three models of it, 7 angstrom thickness, 20 angstrom thickness, and 14, and then 20 angstrom thickness. And with each thickness, we tried to decide what actually happened in the system itself and why did the behavior varied. So the results are shown here in these graphs, and immediately you can detect the outsider here, which is the pure collagen molecule without any hydroxyapatite. But before I examine this, I would first like to define a few terms. Some of you would be more intuitive than others. The first one is strength, and strength is defined as the ability for material to withstand stress without failure or before failure. In this case, this would be the rupture of the collagen molecule and detachment of one strand out of the system. The next term is strain, and strain is defined as the ratio between the displacement of a material, the elongation of it, over the original length, meaning that if I have, say, 100 displacement, then I'll have a rubber band twice as long as the original one that I took. The last term is Young's modulus, and this enables us to tell if a material is stiff or elastic, meaning for a stiff material, the Young modulus would be high because it is defined as the ratio of stress over strain, the amount of stress we have to apply in order to create some certain strain, and for a ductile material, we'll have a low Young's modulus. So returning back to our graphs here, we can show that the collagen in the hydroxyapatite system was stiffer than the pure collagen. And another important feature is that it was also stronger, where the peaks here of disassembling were above those of the collagen. So this was explained through three main failure modes of the collagen molecule in the hydroxyapatite system. The first one was the low-rate plastic deformation. And during this phase, as shown here, the backbone of the collagen is stretched. And while it is stretched, inevitably some of the hydrogen bonds break, basically. And These hydrogen bonds that break cause the small drops in the stress curve, and this is why it's not really a linear behavior, but it is still an elastic stretching. The next failure mode is necking, and necking is defined as excessive plastic deformation. And during this phase, here showing the plateau, the backbone of the collagen stretches and deforms very drastically, meaning that a large amount of hydrogen bonds break. And this breaking of the hydrogen... Oh, I'm sorry. Is this better? Oh. Can everybody hear me? No. Yeah. Okay. Yeah. Okay. Got me? Okay. Thanks for telling. Okay, so the last stage is the creeping. And creeping sounds pretty cool, and it is, again, the linear curve here, and is defined as the slow movement of the collagen or any other material when it is under strain, under stress levels that are below the breaking point, those that would cause the breaking point, but enough to cause it this slow movement, as can be seen here in the movement of the collagen across the surface of the hydroxyapatite. So how does these three main failure modes create a stronger and a stiffer collagen? That kind of sounds peculiar. So this is explained by the hydrogen bonds that form between the backbone of the collagen and the surface of the hydroxyapatite. And this is the aspect which I chose to study. As shown here in the upper row of the stress over strain distribution, and here in the lower row of the hydrogen bond number forming between the deformed backbone of the collagen and the surface of the hydroxyapatite. So for the first model of 7 angstrom thickness, we've shown a linear increase in the strain, meaning a slow plastic deformation. And as this happens, the number of hydrogen bonds also quite gradually increases, resulting with a higher strength overall of the system. This has the highest strength as well as stiffness. For the next model, we've shown that during the necking range here, there is a high amount of hydrogen bonds that form, which makes sense when you come to think of it. A high number of hydrogen bonds break in the collagen, meaning that it will have higher accessibility to form hydrogen bonds with the surface of the hydroxyapatite itself. For the last model here, the 21 angstrom thickness, we've shown also a quite gradual increase in the hydrogen bonds, and this area here is sort of combination between creeping and necking, meaning it varies, and this is what causes the quite gradual also increase, because during the creeping, the same amount of hydrogen bonds remains within the collagen and within the hydroxyapatite and collagen interface. So to conclude, we've shown that through these 3 main failure modes of the collagen, we've been able to create a stronger and stiffer system, and that is due to the hydrogen bonds that create a higher resistance for the collagen to be sheared across the surface. The higher strength was found to be for the thinner models of the hydroxyapatite, and that is also due to the more equal stress distribution in the system overall, meaning that for, say, the thinner model of the hydroxyapatite, there would be a lower Young's modulus. And this smaller distance between the stiffness of the hydroxyapatite and the elasticity of the collagen means that stress would be evenly distributed, and then the necking process would be less likely to happen. Due to that fact, necking process would happen later on in the thinner models, and therefore the rupture of the collagen would be delayed when you compare it to the strain levels that it would happen. The significance of this research, you may ask, is that we've proven here for the first time the enhanced stiffness of the collagen in the molecular level. Previous research mainly studied the enhanced stiffness of collagen fibrils, and the overall enhancement of bone when there's the mineral phase, but not the actual increase in stiffness of the collagen molecule itself. And for further study, we might apply also it to different surfaces of the hydroxyapatite, because in this one we studied only the calcium surface one. Another option to continue this research would be studying the system itself in water, since this was a dry system. I would like to acknowledge several people. First of all, my mentor, Professor Markus J. Buehler. Again, I would like to acknowledge Zhao Quinn, the graduate student who I've worked with, and the people in his lab. Also, I would like to acknowledge my tutor, Annie Young, and all the RSI staff, including Jenny, Dr. Rickard, and any other, and all the TAs who helped me create this slide and paper. I would like to acknowledge Mariana Bedanas, who helped me and taught me MATLAB and create some of these graphs. And Mrs. Salon from Weizmann Institute of Technology, and all my other sponsors that helped me reach this place. And of course, CEE and MIT that enabled this amazing summer experience. Thank you very much.
Are there any questions? Dr. Pashoni?
Can you explain a bit how the simulation actually works?
Yeah, sure.
What level is the population made? Is it the atomic level? How the forces calculated?
Can you repeat the question?
So Professor Kishani asked how exactly stereomolecular dynamics works, if you would like to get more details. Okay, so let's continue a bit. Okay, so stereomolecular dynamics works basically, as I said previously, on both known experimental data as well as theoretical, and I'll focus more on the theoretical right now. So it uses a lot of statistical calculations, say a Monte Carlo statistics. Also, it has the calculation of the energy of the system in total, is of the energies of the covalent energies, the bindings between the atoms themselves, meaning the rotation, the bending, the rotation, bending, and the angle of the bond. Another thing in this specific system that it has is the energy of the van der Waals bonds that form, as well as the electrostatic bonds. The electrostatic include the hydrogen bonds and the Coulombic forces. So this is concerning the energy. Concerning the actual construction of the model, well, for that I obtained the collagen molecule through previous models that one of them was already performed in the lab of the collagen molecule itself. The hydroxyapatite, my graduate student helped to create it we basically cut the hexagonal crystal of the hydroxyapatite into a monoclinic structure. It looks like a monoclinic structure. This is why I gave width, length, and thickness. Another thing, after creating the system itself, you had to stabilize it in order to create the system in equilibrium, meaning that so atoms won't just fly off during the simulation, which is one difficulty that we had during other simulations that we had. After stabilizing it and determining the crystal geometry of the hydroxyapatite, meaning that it's basically stable and that it is how it's found in reality, we had to parameterize the force field. The force field that we used was Charm 22, which is usually used for proteins and organic materials. So that's why we had to parameterize it specifically for the mineral of the hydroxyapatite itself, since it didn't apply and we had to continue more specific steps for that specifically. Again, after we parameterize it for the hydroxyapatite, we again have to minimize the energy. And then finally, we can shear the hydroxyapatite across the surface. With each time step, after we shear it, we put the system in equilibrium, shear it, equilibrium. That's how this time steps works. And then by the end, we have a full simulation of the system.
Nice work, by the way. I just have a question. Were there any points where maybe you made a mistake or there was a setback, something went wrong, and then you overcame it and you learned? Are there any experiences you have?
Yeah. So the question was, what were my setbacks or difficulties during the simulation? So To be honest, the thing that most frustrated me throughout this research was that I was only able to obtain 3 models. And that was due to the complexity of the system, since we had both a protein and the hydroxyapatite itself with the thickness. And I created also more other models of the hydroxyapatite that were thicker. But because the system was bigger, the interactions between the atoms themselves, I had to change them for the bigger models, since I had to change the Lennard-Jones potential and the radius of the cutoff distance of the system. So that was a main problem that created a lot of setbacks considering time that I had to actually study the system. Another setback would be maybe I would have liked to study the system in water later on, which also is quite heavy.
What would you predict to see different when you add water to the simulation? Because with all those hydrogen bonds, that could throw everything off.
Exactly. So he asked, I was asked, what would be the behavior of the system if I added water? What might change? So that is a good question, because water is 10%, and it has a 10%, is 10% of the bone, and we should definitely consider it as one of the materials that could interact with the collagen-hydroxyapatite. And if I'll just return to the simulation, it would be easier to explain. So if we take, say, this last model here. So one thing that I would think about when considering the interactions between the collagen and the water would be first that maybe it might be even stabilized through the hydrogen bonds forming between the water. So I wouldn't know how it would affect the hydroxyapatite itself, the interactions between the interface. That would be really interesting, seeing maybe it would create a more stable system since it would surround it. Or on the other hand, it might unstable the system because the collagen would rather form hydrogen bonds with the water. So I'm not sure how to predict this system, but I think that overall we would see maybe enhanced strength for the collagen molecule. Maybe not considering the stiffness of it, but maybe the strength, because it would be less likely to finally break and rupture. Other aspects I think we could only see after the simulation is complete. Yeah, I plan to continue this. Yeah, this is quite interesting.
One more question there.
So in what context is it interesting to understand the mechanical properties of different thicknesses of hydroxyapatite over this matrix?
Okay, so I was asked why would we test, for the first place, the thicknesses of the hydroxyapatite? Why would it matter? So the thicknesses that I initially studied were 7 angstrom till 21. In bone, it is found between the range of 2 to 4 nanometers, meaning 20 to 40 angstrom. And the continuing models actually will be up till 42 angstrom once they're complete. But the original thought was that during the fracture of bone, so when bone fractures, it is under tensile stress. So maybe it is under tensile stress, meaning, it is under tensile stress, meaning that here it is under tensile stress, meaning the stress is going in this direction. And this stress would be found in the system as shear stress, actually, would come across as shear stress. And the reason we're studying for different thicknesses is because there are different stages in bone sometimes when bone has a less hydroxyapatite that is thinner and hydroxyapatite that is thicker. So we want to study maybe for the thinner model, it's not only because of the density, the amount of hydroxyapatite itself, maybe it's the thickness of it that matters, because previous models only tested the thickness, the density of the mineral. Another aspect for studying the thickness is for de novo materials, because studying bone is really important, but we could also apply this to other aspects of mechanical engineering and copying this biological system to other materials that we might engineer ourselves in order to create higher strength and stiffness.
Thanks.
Thanks.